let me just summarize. So one nice application of Wick's theorem were these matrix models, which you can still think that it's a Tor model for quantum field theory because you integrate over, for example, in this case, two matrices A and B. They are matrices, they are big matrices, but there's no space-time index, right? So they don't depend on space-time. Nonetheless, when you start expanding down the vertices and contracting them with Wick contractions, the graphs organized by topology, what graphs can be drawn on a sphere, what graphs can be drawn on a torus, what graphs can be drawn on a genus 2 torus, and so on. And therefore, even just the combinatorics of these graphs, they organize by topology, so they have this flavor of surfaces, though these are summations over random surfaces. Right? And because of that, if we keep just a single matrix model, that is, if in this matrix model I keep just this A square, and then I drop all this B stuff and I set this e to the 4 beta j to 0, so I really keep just the A to the 4, A square, sorry, and then I keep this interaction vertex A to the 4. In yellow, this would be the single matrix model, right? So I would keep only what is encircled, right? Then it would be a single matrix model that would compute exactly this, but just one here. Okay? Okay? And however, if we give the matrix A and B, because there were two types of matrices and a non-trivial propagator between the two, I could think as A to the 4 as a spin up with 4 neighbors, B to the 4 spin down with 4 neighbors, and the connections automatically encode the coupling between the spins. So just by introducing an extra matrix, going from single matrix model to two matrix model replaces the one by this interesting partition function here. And then we said that a nice question would be, how do we solve this matrix model? The one with surfaces, which should be 1. Then, if it's with surfaces, this just gives the number of graphs of a given number of nodes on genus G. That's like a degeneracy. And then this will be the full energy. It will just be measured by the number of nodes. And this is like the degeneracy of that configuration. And even that model is interesting, so one presentation we could have next time would be for someone saying, so how in practice, so next presentation could be how to solve matrix models, right? So we understood that they compute nice things, but how do we solve them? What techniques can we do to solve them? Okay, so this is actually next to the next. It's next square. Next time, Carlos will tell about Borel. That's tomorrow. Okay. So that's just a summary of what we have seen last time. Today, we are going to go back So today we go back to the Gaussian model. To do the following. So we have seen already formulas, right? We have seen formulas of the Gaussian model equal to formulas of the random walks, right? Partition function were equal, propagator of one was equal to some propagator of the other. The formulas were matching, right? Do you agree? We have seen this. So today, what we want to see, the main thing we want to see is where are the random walks in the Gaussian model? Right? Not just the formulas, but where do we see random walks in the Gaussian model, which was just spins on a lattice. So where are the random walks in the Gaussian model. That would explain why is everything agreeing. It must be possible to reformulate the Gaussian model in terms of random walks. Otherwise, these formulas that we have found so far would be like a miracle. Right? So that's what we want to do today. Okay, so let's go and let's do it. So we start with our partition function of the Gaussian model, which is an integral over configurations which are a spin r, which is real, at each point of my lattice. So there are L square, say, integrations. Imagine it's a lattice, or let's put L to the d, if it's a d-dimensional lattice, and we, for each position, we integrate over r. So there is r to the L over d. And then we have exponential of an action that I will write like this. I will say it's minus u over 2 sum over the sides of s r square. You agree? This was one term. But there was one term that coupled r and neighbors. Right? So we should also write that term. It was minus t over 2. But look what I'm going to do. I'm going to not put the 2 and say that it's sum over edges of, let's say, let me change notation. Let me say it sums over sides. I put an index I. I labels the sides. So this is equivalent to Si, where I is a side. So here I label by a coordinate. Here I just list them all. And it's of course equivalent, right? Then this I runs from all the sides. It's a label of the sides. And now the sides, for each side I, and then there are edges. The edges are neighboring sides I and j, and then here I have Si, Sj. Okay? Why there is no over 2 in the T? So if you remember, there was an over 2 in the T, right? This thing was the matrix A dotted with SR, SR prime, right? And I'm expanding it down in two terms. One I sum over sides I, the other I sum over edges ij, and there's no over 2 here.
You're not overcounting.
Exactly. Because an edge appeared twice, right? Because I have one point, it's neighbor of this one, and when I go to the other one, it's neighbor of this one here. So if I just sum over edges, each edge before was appearing twice. Right? Do you agree? So therefore there's no over 2 here, because this before this edge, when I consider this guy, this edge appears. When I consider this guy, this edge appears again. And I don't want to consider it twice. So when I sum over edges, there's no over 2. Okay? Do you agree? So each edge separates 2 points. So in the language of points, it was appearing twice. Now it's in the language of edges, it only appears once. So that there's no overcounting, there's no over 2. And now we are going to say, well, but what is this thing, Si and Sj, is associated to the edges? And what we are going to try to look is for paths. And paths, what will they do? They will, in this lattice, right? We are after a path formulation. So we are after paths that, like this. What we want to see is paths like this appearing. Right? Where this is an edge. And we want to have some kind of partition function that involves summing over such paths. That would be making contact with random walks where we sum over such paths. So what we are going to do is this exponential. We separate the sides and the edges, because the edges is where the paths are. And therefore, I write this exponential in the following way. I say this exponential is this term here, which I write as a product over I. e to the minus u over 2 si square. I remove the sum to a product. That's one term. Right, so I'm writing what this exponential is. I should close the bracket here. And then the other term is this exponential here. Actually, the t conventional was with a minus sign, so let me put a plus sign there. And this exponential gives me, I expand down, so it gives me for each edge, I now need to expand down, so I need an integer for the expansion, nij from 0 to infinity. I'm expanding an exponential, so t to the nij over nij factorial sj to the power nij. Right? So that's what the exponential is. For each edge, I should do this. So there's also here, I forgot, a product over all edges. For each edge, I expand down like this. Okay. So now I'm going to simplify this edge, this term of the edges. So please see if you agree with everything so far. So now we go to this first row of the blackboard. So now you see that because we multiply at the edges, what we are doing is basically saying that if I have my lattice, what we are doing right now, so far there are no paths, but what we have is the following. So we are saying that we go here and we sum over configurations that can have any number of Sij to the power Nij. So at each edge there is an integer now. You agree? So I make product over edges, and for each edge there is an integer. That can be 0 or can be positive. So it's like I go here and at each edge I choose which integer to put. And if I put integer 0, I don't draw. But if I put integer 1, I draw a line. This would correspond to having n ij equal to 1. Okay? And I can choose this guy, this connection, this one as well, this one as well. I can choose this one. I can also choose to put 2 of these factors, to put n equals 2. Then I have to put either 2 lines or I'll put a 2 on top to indicate that I brought 2 lines. So this would correspond this to nij equals 2. Nothing means nij equals 0. And line means nij equals 1. And for each edge, I choose which integer to put, so I sum over configurations like this. So I'm dropping sticks on my lattice. Right? So I put sticks in all possible positions. Right? I can put a stick here, I can put a stick here, I can make a loop. You see a closed loop here. And so on. So that's the kind of configurations that I describe here. For each edge, I put an integer n. Okay. So that's my configurations that I'm summing over. Right? The configurations are sticks. I just put sticks at each edge. Well, but then what is this? So this thing here, let's simplify just this part here. Right, I sum over everyone. So I sum over everyone. Good. Yeah, okay, there's not much I want to say here. I can say the following. I can say that this is the same. I just want to make a trivial thing. I can, because I multiply over everyone and sum over everyone, This is just notation, but this is the equivalent to saying that I sum over all configurations nij that run from 0 to infinity. Right? That's my sum. I sum over all such configurations. These are these configurations. And for each configuration, what I'm doing is a product over the edges of this. Right? So T to the nij factorial, sj to the power nij. So all this thing here inside this sum is like the weight for that configuration of sticks nij. Right? There's a weight, each way I choose to put sticks, that's the weight it comes in the partition function. Can you see? I see some shiny thing. Can you see the document? Okay, from this angle I cannot. Okay, I guess that's how light works. Okay, so we have this. And now, for each such configuration like this, I have to do the integration over all the s's. Okay? Now, see what happens if I integrate over this s here, on this lattice, this one here. Try to integrate over this s, the one with the ball. What happens?
It's going to give 0.
Why?
Because SI is odd there.
Exactly.
We're going to have an SI.
Exactly. Do you agree? This guy is going to give 0 because this is just n equal 1, so there is just one connection, so the s is downstairs once, alone, and then I integrate the Gaussian, I get 0. So for example, this configuration doesn't contribute. Right? What about without this stick? Would it contribute?
Yeah, because on the exponential, the SI is squared.
Right, so then this integral over each point would contribute, yes, but the remaining configuration, would it contribute without this stick? Well, no, because here you have the same problem, right? This guy is odd here, so this is also not good. So this configuration, even without this problematic one, it's also problematic here. Right? What about here, on this loop? On this loop, things look good, because each side has an even number. Right? So that looks good. So at each point, there are even number of guys getting out. And what about here, on this guy? This guy, it also looks good, because I have Si Sj squared. So it's Si squared, Sj squared. In other words, this is also a closed loop, but it's a closed loop which is very thin, right? So in that sense, it's also a little bit like that. Okay? So what we are starting to see here is that only closed loops contribute. Well, but that's interesting, because then we are starting to arrive at a formulation where Z is what? Is the sum over all closed loops. That's indeed what matches the formula we had found, where the free energy was matching the free energy of the random walk, which was the summation over loops. Right? So let's try to see that carefully. So, right. So, right. So, because, as you say, we integrate over each cusp, it's useful to define for the site I, it's useful to define the nij's that leave from site I, right? So it's how many sticks leave from site I, to define this as ni, right? Which basically, right? So Si will appear raised to the power ni with this definition, right? So it's useful to know because this is what we care if it's even or odd, as Ivan was saying. Right? So we care about integrating over each SI, and we want each SI downstairs to be either 0 or an even power. So SI appears in stick ij, ik, il. So if I sum over all neighbors of I see what the power of SI is. So that's a very convenient thing to define, this Ni. And I could also say that R, let the R be the total number of sticks. Right? Then R is the sum over the Ni. It's really the total number of sticks I have. So in that figure it's what? It's 4, 5, 6, 7, 8, 9. Right? So in this picture, R equal to 9. Okay. Then our partition function is equal to what? Well, sum over R, t to the R, do you agree? T appears to the power each Nij, so it will come with power t to the R. And then sum over all configurations Nij, R can go from 0 to infinity. Then we sum over all Nij that are 0 or positive, right? That are bigger or equal than 0, with the constraint that the sum over all Nij equal to R. Right? Because we want to separate by how many sticks we have. Okay? This is, it is going to be the total length, because each stick is like 1 unit of length, so this is like summing over length of paths. So this is going to be the total length because it's a number of sticks.
Are we overcounting? Because if we have pairs Ni and then J, if I and J are pairs, the edges between both I and J are going to appear both in Ni and in J.
Yeah, that's right. So by this sum, I mean sum over all sticks, right? I don't count, I count edges, right? So I sum over all Nij's. And then I want to argue with the number of sticks. So then I have this. Then I have Nij factorial, right? So I have product over edges. 1 over Nij factorial. And finally, we have the integral over each SI, which is an integral of what? What integral are we doing? We are doing integral e to the minus u over 2 si squared si to the ni. This integral we did before, and this integral gives ni minus 1 double factorial. Remember? This was the number of ways of choosing out of this star with ni how to connect them. This is ni minus 1 factorial. That's if u is equal to 1. If u is not equal to 1, there is some power of u here. Okay? U to what power? Help me out. So I rescale s by 1 over square root of u to get rid of it. Then this is ds. So in total I have 1 plus this. So it's u to the power ni plus 1 over 2. Okay? So what we should do is put product over sides of that. u to the ni plus 1 over 2, ni minus 1 double factorial over nothing, just this. U ni plus 1 over 2, ni minus 1 double factorial. Okay, so here is our formula for our partition function of our Gaussian model. And you see that this term here is automatically, you can see, but here it's automatically 0 if we define it to be 0 if ni is even, is odd. Sorry. So if ni is odd, we set it to 0, right? We need ni to be even, right? So this is equal to this for even ni. And for odd ni, it's equal to 0. So in that sum, we assume that ni is even. Okay, sounds good, right? Now, the claim, what we have to show now, is that our goal is to show that z is equal to exponential of some sum over closed paths. Right? Over single. Right? Single closed path, like a single polymer. Whereas z starts its life as a gas of closed loops. Right? So it's disconnected versus disconnected. So in the beginning, for Z, we have many configurations that contribute, and they can be disconnected from this fixed point of view. We can have, for example, this loop here, and another loop here. Right? These two guys are a closed loop, because they are closed, ni is even. At each side, there are ni in this case is equal to 2 or 0. 2 if it's in a yellow line, 0 otherwise. But it's two loops, it's not one loop. Right? So now it's just a question of combinatorics, and I'm going to show you the first few terms, and just seeing the first few terms you'll be convinced that it works. Yeah. But let me point out that these are obvious configurations, but there are ones that could be a little bit more annoying, so let's do those as well. We could also imagine having configurations like this. Or configurations, okay, one more here. Just to give you an idea that this could be a bit subtle, where I have configuration like this. That is with a 2 here and a 2 here. So these examples, they illustrate something interesting, that here we have an intersection. It's good if we carefully see if there is a subtlety here. And here we have these zigzags, we have these thin paths. So this is like that example over there, but a little bit more complicated. And these are good paths. This is good. This is all good. Okay? So these are the hard configurations. They require thinking a little bit more. And these ones here are the easy ones. So easy just means that Nij is 0 or 1. Sorry, this is also true here. So I want to say that Ni is 0 or 2. Right? At each point there's either 0 lines or 2 lines getting out. This is not true here. Here Ni is equal to 4, right? There are 4 lines. And it's also not true here, for example. Here Ni is also equal to 4. 1, 2, 3, 4. But in these previous examples, in these easy ones, either I have nothing or I have something passing by, and if something passes by, it means Ni is equal to 2, because Nij, 2 and 2 neighboring Nij's are 0, are 1, and that's it. Okay. So those would be the simplest one. Okay, so this is all super important. Don't be lost in the algebra. All we did was we realized that I can at each edge bring down from the exponential an interaction. That means that my configurations, I can think of sticks that I drop on arbitrary edges. I just choose how many sticks I put on each edge, which is how many times I expand this term at that edge. That's obvious, right? I just sum over those configurations. That's this sum here, nothing mysterious there. Once I have this stick language, it looks like I just complicated. Now I have more configurations. Not only I integrate over S, but I choose sticks as well. But of course, the advantage is that the integration I can do automatically. And now I go from integrating over S to summing over sticks. That's obviously the key thing. I start with the integration over S, I end up with summing over sticks. But the integration over S is gone now. It was done explicitly. We did it. It was just Gaussian, it was trivial, we did it. Okay? So,
I have a question. So is the picture too different if when we bring down the t, the proportional to t term, we treat the problem as with Gaussian integration, doing diagrams we were doing before, but with a very simple propagator, with the propagator 2 over u, 1 over u.
yes, that only couples I and I, yes. So it's so simple that we did already the Gaussian integration. We didn't even need diagrams.
Ah, okay.
Okay? But we will go back to diagrams. Okay. Let's see. Is there something more to say here? Okay. So again, this configuration contributes, right? But it gives 4 decoupled loops. What I want to say is that the result should be exponential of summations where I have just single loop. I sum over one loop that can have any shape, this, or that, but just one. I don't have these disconnected contributions, right? So, whereas what we derived was this sum over closed loops, right? Where for each closed loop, I know how to compute its weight. Very easily. Do you agree? So what we have is a class of closed loops, right? Because the NI's need to be even, so it's a closed loop. So I sum over a configuration like this, and for each configuration, you go there and you read off you know the ends from the picture, you compute the weight. Right? So this is what we have. So we have this, right? That's what we have. What we want to see is why does it exponentiate into a single sum of loops. Yeah. Let me think a bit. So let me simplify a little bit this by noticing the following. For each side, U appears, did I rescale U correctly? S was S over square root. No one corrected me, guys. It's minus. Minus. Okay, so U appears at each side. So there is an overall factor of U. So I will correct the formula here. There is an overall factor of U I can take out. That's not very interesting, it's just a constant. Right? And I can, in this way, I hope you allow me to do this. In your notes, you will have to write the formula again. I can remove the 1. And now, for each side, U appears to the ni. So, in other words, if I sum over all powers of U, what I get here is not T, but T over U. And then I can remove the U completely. And it's not square root of U, it's U because of this overcounting that Ivan mentioned. Then Nij appears in Ni and appears in Nj. Okay? So the U disappeared, and it appeared in a trivial factor here, and in an interesting combination here, and we can call this thing alpha, this ratio.
Sorry, how did we kill off the U?
Sorry?
How did we kill off the U again?
So we have this power of U there. This power of U has two terms, Ni and 1. The 1 I just take out, it's a constant overall. It's square root of U for each side. So it's square root of U to the power of number of sides. That I could even put in the integration measure and never consider it. Then we have U to the power minus Ni. That I take out like I took out the T, and it gives me U to the minus R. In the same way that T, when I took out, it gave me T to the R. Good. The reason why it's U that comes out and not square root of U is because each Nij appears twice. That's exactly what you said about overcounting. That's why I fixed the formula for R as a definition as sum over Nij. If it was sum over Ni, I needed to divide by 2. Okay, so now we have this sum here. So let's see. So right. Right. So this is equal to 1 for R equal to 0 plus, if R equal to 1, there's no way I can make closed paths. If R equal to 2, it would give me alpha squared times the only possible configurations with R equals to 2, which would be this, stick up and stick down, plus alpha to the 4, and now with alpha to the 4, with 4 sticks, I have either I make 2 sticks like this, right? Or I make a stick like this. Huh? You agree? With alpha equal to 4. Actually, there's another possibility. I can also make 1, 2, 3, 4. plus, and then there are other powers of alpha. Okay. Whereas, what we would like to claim is that log of z is equal, this is our goal, is to show that log of z is the sum over closed loops. So we'd like to show that this is like alpha square times a single loop plus alpha to the 4 times this loop plus this loop, right, plus alpha to the 6 times this loop plus, let's see, help me out here, plus like this. Here I forgot the configuration, right? So there is also plus, right? Like this two a little bit bigger, so for log of z, and here as well, right? So I can, yeah. By this I mean it can be this or it can be this, right? It can be bent or up, right? They both appear, which is a limiting case of this. It is just this when they are together, right?
And when you count them as different.
That's very important, and we'll see exactly this. That's super important, whether we count as different or not. And we have this, plus, let's draw a slightly more interesting one. Is the one I drew there with 6, 4? No, that's 8, but okay, but this one is 6. This, plus, but just connected, a single connected loop, right? So it's a combinatorial exercise. I think it's easier, it's possible to prove in general that this statement is true. It's just combinatorial, just factorials and so on. Now it's just combinatorial, so there's not much point in doing the general exercise. But I think there is a great point in doing a first examples to convince ourselves that it's going to work. It's more relevant. It gives us more intuition that is going to be important later than a general proof that that box is equal to this expression, right? So it's a goal. Of course, we can start with the box and work hard and prove it. That's roughly sketched in Parisi. You can open Parisi's book and see. But it's just combinatorials, right? I mean, there's no deep thing in proving that that box is equal to this sum, right? This sum has very clear definition, right? It's this, with the same weights that you would associate here, where each term here is just, each graph here would just count as 1. It's already alpha to the 6, right? So each graph here is just counted as alpha to the 6. It's just the length. So each graph here is just alpha to the length of the graph. That's the very simple weight. And you can prove that that formula gives sum over paths weighted by alpha to the length of the path. Okay? That's it. It's just this. So the goal is that log z is equal to the sum over closed paths c. C stands for closed. Alpha to the length of c. Okay? So that's a statement. That's a theorem. And instead of proving it in full generality, maybe we will prove it in full generality. I don't know. But first, I want to see on a few examples that it's working very non-trivially. Okay? But that's the key observation. And once we do this, we explain the formulas. Because before we were seeing that log of z was indeed given by this. Because this is what we compute in the polymers. We summed over random logs with the kappa to the length of the random logs. So of course we know this is true already, right? Because mathematically we already computed this, and we saw that the formula was the same. Right? So we already know this is true. In a way we already proved it, but it's okay. But you could like to prove this from that box, and I understand. So, but since we already proved this, so let's emphasize that. This we already proved it, right? This was already proven, but it was just by formulas, not by combinatorials, right? But we computed the left and right hand side, and they were given by the same formula, and therefore they are the same. But let's see how this works on some simple examples. Because I think it's really quite interesting, quite illuminating. So maybe let's see it here first, in this example here. Okay. So you see that there is this case here, right? Let's analyze that case here. Right? So this term here, if I take the log, I get this term here. That's obvious, right? I just took the log. This is correct. Right? So this is correct. The question is here. Right? The box appears here for the first time, so obviously it's correct. If I take the log, it's correct. So the question is, when I take the log of z, I only get disconnected things. Why don't I get stick squared? Right? So this is what we have to analyze, is these two graphs. They are here, indeed. There is this and there is another one. But they come with non-trivial combinatorial factors, as we are now going to see. And we have to make sure that here they come with coefficient 1 for each of them. Okay? So let's take the contribution of this guy here. Or first, even let's do two disconnected ones. From this formula here, you see that each nij factorial is 1, because nij is either 0 or 1, so this is 1. And at this side, ni equals to 2, so ni minus 1 double factorial is also equal to 1. So everything is equal to 1 in this formula. Right? So this is equal to 1, and nij factorial is equal to 1 everywhere on the lattice. It's 0 factorial or 1 factorial. So this configuration contributes with 1. That's the weight of this configuration. Do you agree? From this perspective, right? For each side I compute this. I have 1, 2, 3, 4 possibilities, but all of them give 1. Right? And for each edge I have this. Right? But these edges are just either 0 or, sorry. Oops, I said something wrong, right? You should correct me. So this is not true, sorry. So here, nij equals to 2. Right? So I get 2 factorial. So this diagram comes with a quarter. Okay. Then it's worth understanding one diagram before. Let's do a single one. A single one comes with a half. Then, right? It's 1 over the nij factorial. And then I'm confused, sorry. Why does it come with a half? Pom 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 pom. Ay, ay, ay. Sorry, give me a second. Okay. Anyway, it comes with a half. This comes with 1/4. That other diagram there, which is 1/2 squared. I think that alpha will be alpha over 2. I will need to put a 2 inside this arc. We will see. I'm sorry. I thought these weights were opposite. No, this is good. And this, let's work out a few more examples. So what about this diagram? What does it contribute with? Where did you get that 3?
The NIJs are always 1, right?
The NIJs are always 1 or 0 outside the lattice, right? 0, 0, 0. So the ones with 0 just give 1, right? 0 factorial is 1. It's nothing, it's just expansion of the exponential. The ones with 1 give 1 factorial, which is 1. That's good. And then, what about this? 2 minus 1 is 1, so it's 1 as well. So it's just 1. Right? Sorry, I need to think a bit. I prepared another example and now I'm trying to do this live. I don't like this one half. Give me a second.
Because when we do the Gaussian integral, there will be a u over 2. So this 2 will come out when changing variables.
No.
Where the u belongs.
No. The over 2 is crucial so that I don't get factors of 2 here. No, I think it's okay. I think this is okay. This is 1, which is 2 times a half. There's no wrong factors of 2. Everything is good. Okay? And the reason is, so indeed there is this unit of 1/2 floating around, 1/2, 1/2, 1/2. And the interpretation here is that paths can have 2 orientations. So this one, if I want to sum over paths, there was this path, and there was the path with opposite orientations. So if I say that each path comes with a 1/2, then I have this path, I have the opposite path, and I have 2 paths that are the 2 orientations. Whereas here, it's the same path, right? Because they go up and down, and there's no difference between the 2. It is just a path where I go up and I come down. There's no difference in the 2 orientations. So we will see that I think this is going to work out okay. So I hope.
And the one above.
Sorry?
The one with the 1 for it.
The one with the 1/4, it's just, I have 1/2 for each loop. And there are 2 loops, so there is 1/2 times 1/2. So.
Oh, okay.
The orientation is 6.
Huh? Yeah. The orientation. Okay. So let's keep this formula here because we have to fix it, as clearly we see now. So far, these were some simple examples. Let's see one more example. Okay, I think now we are finally ready to see a more interesting one. Okay, let's see this one. Now this one, is more interesting. It has Nij equals to 2, right? As we said, Nij equals to 2. So it comes with a 1/4 as well. Right? But now here, what factor do we get? Extra factor here. Here Ni is equal to 4. 3 double factorial, which is 3. From the Ni equals to 4 at that point.
I'm sorry, in all of these examples, each I involved in the diagram has had the same Ni. Okay.
That's right, but not in this one. This one has Ni equals to 2, this one has Ni equals to 4. Now, here comes something important. That why do I think of this diagram like this? All I know is the sticks. There are 2 sticks here and 2 sticks here. The fact that I drew it like this was a bit too much. The way I should have drawn it is like this. I should have said, this is one possibility, but there is another one where I have just 2 disconnected loops. And there is another one where I have this. In other words, these 3 came from the following. I had a vertex here, which had 4 lines, which had 4 points, and I had to choose how to connect them. Right? And I had to choose how to reconnect them. And so, if I say that these points, when integrated, if I do this recontraction, where 2 of them coupled to 2 of them, which are like this, then I get this, I can interpret the result as this graph. If I say that this connects with this and this with this, it's this graph. And if here I swap 2 of them, I get this cross graph. Okay? And so we see that the same contribution, the same configuration here, it's more natural to split these 3 and to say that this 3 is 2 plus 1. Right? Where the 1 is this special guy, which is 2 disconnected guys. You see? So now we see that we get 1/4 for 2 loops, even if they are together. And that's the one here. You agree? But this gives, so let's write more carefully, this gives 1/2 plus 1/2 squared. So this 1/2 is a single loop. Right? This gave me a single loop. This and this are the same. They're just. So that's a single loop. Right? Where I do like this, and back. I go up, up, and then I come back, back. And these are 2 loops. Where I have 2 loops, they just happen to touch at a point, where in one case I go up and down, in the other case I go up and down. I just separate, you see nicely, these 3, it nicely separated into 2 and 1. And then when I do it, I get perfectly what I'm starting to see appearing, which is 1/2 for a loop, 1/2 square for 2 loops. Right? And here, 1/2 square, because it was 2 separated loops. Okay? And here, 1/2 because it was 1 loop, and 2 because of the 2 orientations that we start having only when the diagrams are fat. Okay? So the fact that I can interpret this graph in 3 ways, right? The fact that I can split these 3 into these 3 ways, is the logic behind why it was 3. Because it was the number of ways of doing weak contractions. But we don't need to do it to know it. If we know the number, we can just split it ourselves and interpret this in this way. That's what we need for the combinatorics. Okay? So let's work let's work one more example, because now we are starting to see that the combinatorics come out okay, but it's crucial to interpret sometimes a path as 1 or 2. Let's analyze this one here, the one that I did not erase. Let's analyze this. So this diagram gives what? What's the weight that it gives? It has Nij equal to 2 here and here. There are two places where Nij equal to 2. So that gives me 1/2 squared. That's because, as we said, there are two places where Nij equal to 2. Right? And otherwise, the Nij factorials give 1. And then, what else does it give? There is one place here with Ni equals 4, one with Ni equals 4. So what factor multiplies this? For this diagram?
3 twice 9.
Exactly. 9. Okay. Now, we know what we should do. I should split this 9. Now let's split it in a clever way. So let's see it by the graphs. We can just write numbers. I can just explain. I think I want I will not to guess. I will draw the picture and explain. So this graph I can interpret like this, but it actually breaks down into 9 graphs. So let's draw the 9 graphs. So one is this. Now an extreme one, which is the extreme opposite, is this. You see, what I interpret now as 3 disconnected components. Right? It's just the same graph. This graph also has, and these loops I could split it like this. But there are also other possibilities. There's also this one. And there's also this one. And you see that here I can also twist this and reconnect, but this is the same graph. It is just in the bottom I reconnect in the other way like we did in our example. And here I can also twist, and here I can also twist. So here there are 2 possibilities here, 2 possibilities here. So either I twist here, or I twist there, or I twist in both. So this graph here would give 4. This graph will give 1. This graph would give 2. And this graph would give 2. Right? So that's just my interpretation of this 9. Okay? So let's see that this is beautifully working. So in total, this 4 times 4 is giving 1, which is 2 times a half, 2 orientation. And the half is because, as we see, each loop gives a half. That's something we are seeing. Do you agree? I multiply 4 times 1/4 is 1, and 1 is 2 times a half. Right? By this arrow I mean 4 times 1/4. What about this one? This one becomes 1/4, which is 1/2 squared. Which I want to write as 1/2 cube times 2. 1/2 cube because I have 3 loops, and 2 because there is orientation of the square. Right? 2 is the orientation of the square. And that's how I write the 1/4. This 2 is 1/2 that I write as 1/2 square times 2. 2 the orientation, 1/2 square, because there are 2 loops. And the same thing here. Okay? So again, normally I would have this configuration and this one separated. And if they are separated, the weight is very simple. I'm seeing that if I want the configuration to be the same when I put them together, it's fine. Then this, and this are disconnected contributions. They are just the limits when the things are far and come together with the corresponding weights. Then this is the new guy, and this new guy is coming with a perfect weight. Right? So finally, just one more example, and after this example, I conclude that we proved by exhaustion. So let's do one more example, which is, for example, this. What happens here? What's the weight of this graph? Guys, what's the weight of this graph? 3. Is 3 correct? 3 is correct. Can you explain why?
Because all the nij's are 1, but there's one
Good.
vertex which has an I equals split.
Okay. So 3. How do we split this 3?
So that 3 is, there's only one loop, right?
Here, it looks like there is.
Oh, no, but
Is there a
you
loop?
can break it into 2 different boxes.
Yeah, exactly. So let's split this 3. We can say it's either this possibility, or it's it's this, where the loop does this, right? Or this, right? So I should split 3 into really 1 plus 1 plus 1. Because this path and this path are really different paths. Right? It's not like here that these paths are the same, they go up and down. No, those are different paths, right? And now let's see that it works. So let's see once more. This one here, the disconnected one, I want to say that this is 1/2 square, because there is each loop give me a 1/2. But each one has an orientation times 2 squared from the orientation. Okay, perfect. This one, I want to say there is one loop, so 1/2, and one orientation 2. And this one the same. Okay? So conclusion. Once we separate this nij factorial, what this guy does is at each intersection chooses way of reassembling things. And it does such that the final result that we get is what we are getting is that z is equal to the sum over r from 0 to infinity, summation over the number of loops n is the number of closed loops, right? Then each closed loop, we can say it comes with a factor alpha over 2 to the power of the length of that closed loop, right? So if we use r, maybe we can use here RC, where of course the I wrote something wrong, sorry. Let's be careful. So alpha to the length RC, number of closed loops, so 1/2 to the power number of the closed loops, that's what we are saying. Each closed loop always comes with a half. I sum over closed loops, and alpha to the r. Let me not change. Alpha to the r. And number of closed loops, and then for each closed loop, I sum over the loops. Right? You tell me what's the total length, how many loops you want, and then I have to sum over where these loops are. And that's the conclusion we seem to get.
Was there was a moment where, for example, considering the simplest diagram, the one that's accompanying alpha squared when we expand it z, there's a point where we stop caring about where the two sticks are, but what the specific eyes that where they're attached. I mean, I can translate that diagram over the grid.
Right. So I sum over all possible loops. So there is a factor of the volume that appears. Right. So that's it. That's here. It's in the sum over loops. Right. You tell me the total length that I can use, how many loops you want, and then I have to sum over all possible loops with those constraints.
Okay.
Which means weighting them with alpha to the total length, weighting them with 1/2 to the number of loops, but summing over where the loops can be. So indeed, this diagram here can be anywhere, so it can be multiplied by a volume. Now we want to do one more step. We want to say that this is equal to the sum over, I want to exchange to sum to the number of loops, number of closed loops. And now I want to write a formula like this. I want to say that for each closed loop, what I do is I sum over the length of that loop r, alpha to the r with a 1/2, and I raise it to the power of number of closed loops. Okay, so let's see if this works or not. So the problem is that this is a single closed loop. Here is single closed loop. Okay, but when I square, imagine I have two of these guys, right? Imagine I have two of these guys. So when I'm summing here, I'm doing a single loop. So the single loop, I have this configuration plus, and then this configuration here, right? I have these two configurations. I don't know why I changed color. Square, for example, if I have two loops, right? Now you see that from the cross term, when I open up the square, indeed, I can get this guy times this guy, but it comes with a factor of 2. Right? But they are indistinguishable. This factor of 2, no one ordered. We were not putting factors of 2 or anything when there are two loops. We just see two loops, we are just counting the weight. Do you agree? So what do I need for this formula to be true in the last line?
1 over n e factor.
Yeah, it's not an e, it's a c from closed loops. 1 over n c factorial. Right? Because I don't want, then this is true. If I sum loops and I square, I don't get overcounting. Right? So this is 1 over n c factorial, precisely because this gives me twice the configuration that I want, which is this squares, but I want to kill the 2. Right? So we went from here to here. Now I have an exponential. This is the definition of an exponential, so we just prove this. And apparently there is a 1/2 here. Okay. Okay. Any question here? Is everyone happy with this formula and with what we did next? So next what we did was, for each loop configuration, we see that if the configuration is easy, the weight is 1. Right? So for all easy configurations, which don't have any n equals 2, things are just 0 or 1 factorials, weights are just 1. So easy configurations just give 1. Right? So easy configurations just give 1. And by easy, we mean without zigzags. So if I have a configuration like one loop like this, and then another one like this, right, and another small one, right? These 3 loops, the weight of this is 1. What is 1? Is 1/2, 1/2, 1/2 times 2, 2, 2 from the orientation. So those combinatories for the easy ones are obvious. They just give 1, and 1 is 1/2 times 2 as many times as we need. Right? 1/2 for each loop, 2 for the orientation. The subtlety was when we start drawing graphs that can be interpreted as many things. Like this configuration, this is just one spin configuration, right? This was just bring down this edge once. So this, all nij's are 1. So from spin point of view, it's clear. We are just considering one interaction between ij, jk, jl, jm. That's clear from spins. But in paths, there's an ambiguity, right? We can think of it like this, or like this, right? So if I want to sum over paths, this is 2 paths, this is 1 path. So if I want to split it, okay, this is 3, I have to interpret what 3 means. And 3 means 1/2 times 2 times 1/2 times 2, it's 1. 1/2 times 2, 1/2 times 2. Okay? And then it also works. It gives 1 plus 1 plus 1, the sum of closed paths. Right? And the theorem, the question is it true that any term that I write there, just based on this interpretation of the n(i-1) double factorial is number of ways of reconnecting things, is it obvious that the combinatories always come out beautifully like in the examples we did? Right? And that's just combinatories. You can just work with factorials, you can consider some more complicated examples, and but I would say that for now, this is enough. If you want, we can do one more example to see if it works. You want to do one more example? Okay, so tell me one graph. If you can. We never did one with 3, for example. With, I don't know, the propose something that's not too painful, but. Do you have anything in mind? We already did intersections, we already did zigzags, but we only did nij equals 0, 1, or 2. I don't know.
We do three, like 1 ni with 3, and those 3 sticks connected to a square.
Okay. For example, maybe, let me see if this is what you mean. This?
No, I mean one of the ni's to be 3.
So this ni is 4, this ni...
Yeah, I'm sorry, one of the nij's.
The ni's cannot be 3, right?
Yeah, one of the nij's.
So, for example, this diagram, let me just say one thing. So this diagram, naively said it's not possible because this ni is 3, right? But if I say that this line is double, then this I think is possible, right? And now this diagram, but this is a very painful one, right? It could be interpreted in many ways. Right? For example, one way is this diagram, I could think of it like this. It could be, for example, this, and this. That's an example. One diagram. But there are many other possibilities of reconnecting this into loops. Right? Plus dot dot dot. Now you were saying something else. You were saying one edge which has 3, and then?
And then connect one of the vertices to a square.
One of the vertices to a square. Why not just make this, for example?
Yeah.
Okay, you prefer this?
No. I thought about that, but that doesn't work because the vertex where it's connected there, it has an I equals 5.
So here it's 5. It doesn't work. Right. So this one would not work.
Yeah. But the one that you did before.
The one I said works. Okay. So let's try to work this one out. It's a good example. So this is what? So this is 3. So it comes with 1 over 3 factorial, right, from this Nij. Then these Ni's are boring, but this Ni is 4, so it comes with 3, and this Ni is also 4 with another 3. So in total, this gives 3 halves. Right? So 3 halves. We have to interpret these 3 halves. So let's try to split these 3 halves into what? So we have, for example, a square together with a loop like this. That's a possibility, right? Another possibility would be I start like this, this, then go up. Okay. This is another possibility.
Could you have the external, so you have one big square and one rectangle. Could you have the rectangle inside of the square?
That's the same thing. There's no difference, right? It's just, I mean, I'm splitting these 3 points. These 3 points are at the same position, right? All that matters are to up, down, and I make a square. And there's no meaning to this being inside. And here, it just means that I go up, then I do a square, and then I go up again. And then I come down. So there's also no meaning in reshuffling these things here. I think that's it probably, no? Is there something else?
You have two orientations in the first one.
But I think it's only 2 graphs, right?
Yeah.
So now let's try. What weight would I like? I will not see these 3 halves. So what weight would I like here? 2 for the orientation, and here 2 for the orientation, and here 1/2 times 1/2, because there are 2 loops, and here only 1 loop, so 1/2. So in total, I would like 1/2 plus 1, which is indeed 3 halves. Do you agree? Okay, so it's really, this formula is really true. This was proved, as I said, by exhaustion. Check on many examples, and you can work on more complicated examples. You see it works perfectly. This is exactly the way we get. But then if this is true, we prove this, and this is, by definition, is exponentiation.
I have a question.
Mm-hmm.
This map between Gaussian model and random walks works order by order, but works for non-perturbative as well. If you only with path integral, and if you could do it exactly, you match both sides.
That's right, because we did it, right? That's what we did. Right, we did the Gaussian integration. Okay, so yes, it does work. The punchline is that indeed, it's exactly what I wrote. Okay, there's a factor of 2. There's an overall 1/2, but up to an overall 1/2, indeed, they just come perfectly with weight 1. And that's how we get all these graphs. Okay. Now, I would like you to tell me. So this is how we see that the Gaussian model. So we established that the Gaussian model is a soup of closed polymers, right? So what we said is like the Z of the Gaussian model equal to the Z of a gas of polymers. Right? Which is exponential of the free energy for a single polymer. Single random walk. Right? So this is what we established. We did it by formulas before, and today we did it by combinatorics using a little bit of Gaussian integration. So this was equal to this, which was equal to this formula. Right? Now, question, what about the propagator? Si, Sj. Right? So now, I want you to tell me what's the final formula. Now it's a similar thing that I want to compute, except that I want Si, Sj. So I want to put a spin Si at position I and put a spin Sj at position J. And then repeat the same analysis. Repeat exactly the same thing, where in my derivation I start, instead of just the empty Gaussian integral, multiplying the exponential, there is this Si and Sj. Right? So that's exactly the same starting point with this inside the integral. Do you agree? What changes? Can you tell me directly the final formula?
I can't tell you, but there's a key thing that changes from one of the first things that we did at the beginning of the class, which was saying that if I threw down an odd number of SIs, it would give 0. Now, throwing down an odd number is really throwing down an even number because we have an extra SI.
Exactly. That's super important. So what Ivan is saying is that, so would this be okay? Yes, because this is closed. That's fine. The problem is this spin is odd. Right? So this spin is odd, so if I integrate over this spin I get 0. So not to get 0, I need to bring down an odd number of edges, for example 1. Now this spin is even, because it appears once outside and once in the link. But now this is odd. So now I need another one. Oh, but now this is odd. Now I need another one. Right? So, and here the same thing, right? So you see that what happens is that this is good. Right? So what I have is a closed loop from A to B plus any number of closed loops here. Right? And these loops, okay, as we saw, they could also, this loop, let me add something here, it could, perhaps with things like this, right? That could have some self-intersections.
But I could also have closed loops that start and end at A? Oh,
No. You cannot, right? You agree? If I put a square here, then the cusp A is 3. So that's it. So that's the configuration that contributes, right? So I called it A and B, so let me put here A and B. So what will change in that formula? There. So, this statement that I sum over this type of configurations is true. Just bring down from the exponential any number of NIJs. For each edge, I bring its expansion of exponential, I get NIJ factorial. That doesn't care about what I'm averaging. Each side, when I integrate, gives me an I-1 double factorial. This is true, definitely, if I multiply over I not equal to A and B. If it's not A or B, the rest is the same. Right? You agree? What about A and B?
I will get NA plus 1 minus 1.
Exactly. So, for I would get NA double factorial, NB double factorial. Because for those there's an extra spin there put by hand. Okay? So with this yellow stuff, I get this expression.
But don't
We need to divide. Good, good. So this expression is equal to the yellow stuff divided by the white expression, which is the partition function. And now it's just a question of simple combinatorics to see that when we do it, what happens is that by doing this division, we cancel all closed loops. The closed loops are there in the white stuff, so I divide by it and they cancel out. Okay? Because I already erased it. But remember when I wrote this formula, which was closed loop to the power n over n factorial? The analog formula that we will write here is the sum over one open loop from A to B and n closed loops then there would be some alpha to the length of the open loop open from A to B. That's the weight of the open loop. And then the closed loop would be the summation, a sum over this length. That's the open loop, L of open AB. And then I have something to the power of n closed, 1 over n factorial, n closed factorial, alpha to the length of the closed loop. And I sum over this length. So I'm being a bit sloppy. Sum over n. I'm summing over n, which is the number of closed loops. And I have one open loop. Then here I'm summing over all open loops. And here I'm summing over all single closed loops. Okay? But you see that this sum factorizes and it becomes equal to z, the partition function we already computed. But this we divide by z, so this is 1 over z. So it's z to the power 0, this cancels, times sum over open loops from A to B, alpha to the length of the open loop from A to B. Okay? Again, by the same reason that the various loops don't talk to each other, like before, because of the combinatorial. So this guy, for example, you can interpret as an open loop and a closed loop, or a single closed loop, and you work out your combinatorics, and they are such that they are not interacting with each other. They don't care. So it is just a single one to the power n over n factorial for the indistinguishability of the closed loops. But then it means that z factors out. Okay? So we show that the propagator is a sum over open loops, alpha to the power of the length of the loop. So we show that the propagator as A as B equal to the sum of these open polymers, which was again something that we also knew by formulas. We already showed that the propagator was equal to the propagator expression we got, and here we see it in this graphical very explicit way. Right? So we knew, again, by formulas, not by pictures. Okay.
When you say that, you mean that that we had calculated it for the random walk, where it
We had calculated it,
calculation, and then the Gaussian model gave the same formula.
Yes. So we computed for the polling, for the random walk. We even computed for the random walk in many ways. Either by computing a formula and matching with the formula of the propagator, or because we saw that this obeyed an equation that was the same equation as the propagator obeys. The propagator is the inverse of a matrix that was following from a recursion relation for the random walks. So we proved this equality of the formulas in many ways. We even saw that the final formula is not only the same, but the equations that lead to the final formula, like inverting a matrix, is also the same. And now we see very explicitly where are these paths coming from. It is just that summing over spin configurations is really the same over summing of particles that go from one point to the other. And they can do everything that the random walk can do, come back, do whatever, and we see that the combinatorics work out perfectly. So it's not just that the final formulas are the same, it's really that the sum over configurations of spins are the same as configurations of walks. I give you a walk, you can reconstruct a term in the partition function of spins. Right? So they are really the same model in this case. So it's 12:40, and normally I said we'll stop at 12:40, but I don't want to do what I wanted to do now next time because it's a bit too boring. I want to do something that for many of you it should be trivial, but if you want, this is a little bit of homework, and I want to give a hint on how to study this, which is, so what is the long distance behavior of this propagator? So this propagator, I want to estimate how the spins correlate with each other at large distances. So this part is unrelated to everything we did before today. We said that if I have a position I, position j, and Ri minus Rj is R, then this propagator, right, when R is large, right, we said that if R is large, this propagator is roughly integral d dq 2 pi to the d, this is just a constant, it's not very important, e to the I q dot R over m squared plus k squared, where this m is related to t and u, and there might be a constant here, but after we rescale things, we get something that we call m then. Right? So we have seen this formula several times, and my question to you is how do we estimate the behavior of this propagator at even larger distances, that is, when distances are measured in units of this mass, that's dimensionless, when this is very large. Right, so how do I estimate this behavior of this propagator, this type of integrals? If you already studied some quantum field theory, you might know, or if you know some Fourier analysis. So that's the question, is how do we estimate the behavior of this propagator at large distances? So I have my lattice, and I have a spin here, from very far away. Right. So really many lattice separations away. This should have some smooth limit, right? And then I just have a smooth table from very far away. And I want really large distances to study what's the propagator in some continuum limit at very large distances. We expect the correlations to decay, to go to zero. How do they decay, and what's the behavior of this propagator? Okay. So who knows the answer to this? To compute it mathematically, I have this integral, I want a large R behavior of this integral.
Well, the easiest way I think is that the integral is related with some Henkel function. I think so. You pick the Henkel function and see the behavior of that function in the large R values.
Okay. So this is a question that you should clean up and know everything there is to know about this behavior. It's very important, because this is the simplest correlation function in a statistical model and in quantum field theory. And the simplest question we can ask about it is what happens at large distances, right? So one way that Victor is proposing, he's saying that actually this integral can be done exactly, right? And the integral gives some Bessel function. And then I can series expand the Bessel function in Mathematica, say, and get the behavior, and we would conclude that it decays exponentially with the distance. Okay, that's true, that's good. We can do the integral. How do we do the integral, by the way?
Do spherical integration up
Right.
to the angle.
Right. So this will do going to spherical coordinates. So if we go to spherical coordinates, it's easy to see that this integral is easier to do. You can just indeed massage a little bit, you get some Bessel function. I recommend that you clean this up. What's the advantage of this method? Well, it's exact, as exact as it could be. What's the disadvantage?
You have to have the exact solution.
Yeah.
If you cannot.
And I don't know about you, but I don't have too much intuition about Bessel functions. So how do you do if you don't have a Mathematica or if you don't have a book? How do you derive it without a book?
I think I'll try to expand for small k and interview.
It's already expanded at small k. Remember that we got this expression at large distances because we had some cosine of k mu, right? We summed over mu equal 1 to d, and we said, oh, this is basically a constant plus another constant times k squared plus another constant times k to the 4 plus, right? And we already said I only keep the k squared because I'm at small distances. But you see that there are two things. One is distances much bigger than the number of sides, but then there is really big distances. So we are taking yet another large distance limit. It's even larger now. We already went to the continuum limit. That's why cosine became k squared. Now in the continuum, in the table, I no longer see that there is a lattice. I can still now approach the points or take them apart. I want to take them apart in the continuum. Okay, so expanding at small k, you could think that you drop this k. If I expand further, I expand small k, I bring, what way do I expand small k? And it becomes like r downstairs. Right, so that's very wrong, right? Because if I start expanding, then the integral doesn't converge, it's not giving me this exponential, and that's just a bad idea.
Can you just try to make a substitution in putting the spherical coordinates, so the exponential will be modulus k times modulus r cosine, and you can do a change of variables, say that some letter equals k times
Okay.
r.
So that's one direction, it's the direction of spherical coordinates, so let's do that. So let me do that. So let me say, but I'm going to do it a little bit schematically because I leave it up to you to figure out all the factors of pi. So this is absolute value of k, absolute value of r, cosine of the angle, right? So if I have r here, k is here, and there is an angle theta between the two, right? And then this is particularly nice because then this integral becomes integral. Let's first write the integrand, e to the I. Let me call this absolute value of k just k, absolute value of r is just r, cosine of theta. Then the propagator is just k squared plus m squared. This seems to be good, right? Now I have to integrate over k, and I have to integrate over theta. Right? So notice something, that the result just depends on the angle theta and on the magnitude of k, but I started integrating over the variables k. But all that matters is the size of the vector and the angle with respect to r. Right? So the other integrations are just some volume, of some sphere. So there is some volume factor here, right? And then there is integral radial coordinates. So if it was 2 dimensions, it would be r, 3 dimensions r squared, more general it would be k to the d minus 1, right? We agree, in spherical coordinates, d theta sine theta times that. Okay, so that looks good, because the integral over theta I can do. So I can write that the integral over theta, sine theta is the derivative of cosine, so it's perfect. I can just do the integral, and we get some volume times an integral dk k to the d minus 1. The integral gives me e to the I kr minus e to the minus I kr divided by kr, and then I have k squared plus m squared. That's the integral over theta, right? Which I can write as the difference of two integrals. So I can say this is like I plus minus I minus, the two exponentials. Right? And what Vieira is saying is that this integral now is a Bessel function integral. So this integral over k, you see this k minus 1 here with minus 1. Sorry, I have to multiply, and it's okay. So this becomes just k minus 2. This r is a constant, I don't care. So it is just k to some power, k squared plus m squared downstairs, e to the I k, and that's the definition of a Bessel function. That's an integral representation for a Bessel function. So immediately you can write this integral as two Bessel functions, which you can further simplify into a single Bessel function using parity, and that's it. That's the result with a Bessel function.
Now instead you can do a clever substitution in the exponential and put it as a function of something over a function of r and expand in Taylor series.
Okay, so we went to this integral, and now, as we said, we could go to Bessel, or we can do something smarter. And now we want to do something smarter, which is to estimate the large radius behavior of this integral, and let's see what Vieira is proposing.
For to do that, you have to do some substitution, like u is something 1 over r.
But first, yeah, okay, let's do that. Do you agree with this? Everyone is happy with this? Okay. Now you are proposing u equal
something to put for large r's, you have a small u for do a Taylor series around u equals 0. You get it?
So you want to do u equal k times r?
No, the opposite of it. U equals the inverse of it because it's more easy to do a Taylor series at 0 than at infinity. So you want some variable that for small values it's equivalent for large values of r.
This is an integral over k. It has two parameters inside. It has r and m. Okay. In fact, if you rescale k by m, then here it becomes k squared plus 1, m gets out, and here becomes m times r. So right away we see it's actually just a function of m times r, as it should. Right? So you can set m to 1 or ignore m. So it's a function of r. So what change of variable are you proposing for this k?
Just not the k is just you.
I just want to continue with one thing. So this is a constant integral dk k to the d minus 2. I just want to simplify a little bit. K squared plus m squared e to the I kr plus complex conjugate. Okay?
1 over r.
Sorry?
There's a 1 over r.
1 over r is a constant. I took out. If you don't like that, it's over. Okay. So the question is, how do we estimate integrals like that one at large r, when r is large? So this is just mathematics.
If R is large,
There's no
the
physics.
phase oscillates a
Very
lot.
good. R is large. This guy oscillates a lot.
Then you can do stationary phase oscillation.
Exactly. So when K is very large, this oscillates like crazy. Right? When R is very large, so when R is very large, this integrated oscillates like crazy, unless K is very small. Right? So clearly the K that dominates is K, looks to be K very small. So, so we want to see how to estimate this integral. And the idea is to think that this is going to be, I'll do it sketchily, it's integral dk. Okay, this k to the d minus 2 turns out doesn't participate in the saddle point, but what does participate is the following: e to the I kr minus logarithm of k squared plus m squared. Okay, if you want, you can put the d minus 2 log k in the exponent as well, but it doesn't matter, we will see now. Now you see that when r is large, you integrate from 0 to infinity, but you look for a saddle point, right, because it's oscillating a lot. So what's the saddle point equation? So the saddle point, stationary phase of saddle point, tells me that derivative with respect to k, which gives me I times r, do you agree? Minus 2k divided by k squared plus m squared plus that term that doesn't matter equals 0. How do I satisfy this equation when r is huge? So r is huge, is a million, and you want to put a million equal to something small
There is something small.
divided by something small plus 1. Not true, right? A million is not equal to a million over. Isn't a million is not equal to 0 over 0 plus 1. So how do I satisfy this equation? How do I make this term very big? How do I make 1 over x squared plus 1 very big?
X small.
No.
Large.
No.
X of order 1.
No.
There's the 3 limits that it's possible
Big X,
to do.
imagine.
Exactly. 1 over x squared plus 1 is large when x is I.
Yes.
That's how we make this. So what solution do we want? Is k I times m. When k is close to I plus m, so this implies that k is close to I times m. That's the singularity that makes the saddle point large. Right? It's proportional to I times m. Okay, plus some small correction. So it's nearby I times m. It could be plus minus, right? It could be plus or minus, but we'll see that one sign will give an exploding result. And if k is I times m, then this integral, k is I times m, is proportional to e to the minus m times m. Because that's the value of k that is the singularity, is k times m. Okay? And you should have guessed it, because it's always like this. Large radius behavior is dominant by the first singularity in the complex plane in Fourier. And the first singularity is k equal to Im.
But if we try to do a residue integration once we've integrated over the animals,
Now we are here. Now here you have an integral from 0 to infinity. So you cannot use residues. It's not from minus infinity to plus infinity.
well, why can't I use residue there? I do a quarter. I don't do a whole half circle. I only do a quarter of a circle.
So you can rotate the contour, right? Then after you rotate the contour, yes, you can pick this pole, and that pole will give this convergence. Yes, you can do that. and then you have to continue manipulating further the contour to show that the rest is exponentially small. So yeah, that you could also do. And that's basically the reason why this is the correct behavior. That's another way of saying. You have to be careful though, right? Because you have k to some power here, d. This d is a priori not even an integer. It can be whatever you want. Contour manipulations, when you have these funny things, it's a bit more tricky. But what we did is perfect. So we see it's e to the minus mr, which is what the Bessel function would give. Now, what about the prefactor? Well, for the prefactor, you have to work out carefully all the Gaussian prefactor integral. That's why it's homework, but I'm giving the main ideas such that anyone can do it. Right? But I really think this is very important. So it's really important that you sit down at home and clean up what I'm now explaining. I think I'm giving enough ideas that it's very easy to clean up, right? You understand, you go to spherical coordinates, so what do you have to clean up? You have to clean up why this volume, why this power of k, why this sine theta, the rest is obvious. Then you have to explain, to clean up that this is the saddle point. For example, we see that this term here gives a constant at this saddle point. Right, so it doesn't matter for the saddle point, but you have to clean up that this term is not contributing, that is not shifting this value, because indeed this term is finite at this value, so this is exploding, these are the two terms that matter. So you have to clean that up. You have then to compute the prefactor of the Gaussian integration, right? The Gaussian integration doesn't give just the value at the saddle point, it gives the prefactor as well, right? When you do Gaussian integration, which is just the 1 over square root of u that we were doing before. You just expand it on the Gaussian. You put everything together, and you will get that here it's some power of r. But the power of r is not as important. Exponential is really the leading behavior. And you can even compute the constant as well. That's another. This is what I mean by cleanup. You can also find the Bessel, and you can see that you get exactly the same thing. That's also cleanup. So there is a lot that I really think is very important if you want to use quantum field theory in your life, that you did this kind of manipulations very carefully once.
That volume term, are we going to be able to calculate without assuming that d is an integer?
Without assuming what?
That d is an integer.
Well, you can assume that d is an integer, compute, and analytically continue, but yes, you can compute for any d. Yeah. Let me show you another way of computing that I think is quite useful to know as well, which illustrates a little bit this notion of the first singularity in a complex plane, which is to say that I suppose this is isotropic, so I don't lose any generality by thinking that I have my particle in the direction x, right? dkx over kx squared plus the other k, the other components, plus m squared, and I have to integrate over d minus 1k, where these are the other components. And here it's just kx component. And so let's suppose, for example, that we are in 2 dimensions. So we only have kx and ky. Okay, in this way of doing it, and we can later think about general dimensions. Then what does the integral of ky give? Huh? No. Or yes, but that's not how you want to do. Obviously. Okay, these are all integrals from minus to plus infinity. So let's do this integral in a few examples. Let's start with 1 dimension. one dimension, there is no other. There is nothing. There's only kx. And then we are doing what you said. Integral dk e to the I kr over k squared plus m squared. How do we compute this integral? By residues. There is a residue at k equal to Im and a residue at k equal to minus Im. Which one do we pick? Plus Im or minus Im?
Plus Im.
Plus Im, because then I times I is minus. So this is equal. We pick the residue at k equal plus Im. So this is just e to the minus m times I. Okay, so that's one dimension done by residues. Two dimensions. In 2D, the integral over ky I could do. Now I have two options. I do first x or first y. So let's suppose we do first ky. If we do ky, the integral over ky, I have a residue at square root of the rest times I and minus square root of the rest times I. Do I close up or down? Doesn't matter. Any is the same. So I do the ky, I pick the residue and I get integral dk e to the I kr divided by square root of k squared plus m squared. Do you agree? I just took the residue of ky. Right? Ky is 0 at plus minus I times the square root. And you see that this is an integral over the real line where there is the square root cut at Im and the square root cut at minus Im. Right? In the remaining k plane. So the analog of moving the contour up, whereas here I have an integral with a pole up and a pole down. And what was smart to do was to move and pick the pole. So I want to do the same, but now I have a cut. So what should I do? I move and I surround the cut. That's as much as I can do. I cannot just pick it, I surround it. Because then when I surround, you see that k is Im, but Im gives me e to the minus r. Right? So then it's smart to say that k is Im. I plug here, whoop, it's perfect. Plus it, where t is this variable that now moves me along the cut here. Right? So we conclude that the integral we get is equal, after we do this shift, as I said, e to the minus mr, perfect, outside, times integral dt, t now because I wrote k equal I plus t as a cut starting at 0, and I'm doing this integral around this cut, and there is another cut here, which is this cut here, starting at minus 2m. Right? And I have this integral over t on the cut, but the square root on both sides of the cut is the same, up to a sign. So this is twice the integral like this, which means from 0 to infinity of dt e to the minus rt divided by square root of t 2m plus t. That's just the square root shifted, right? And that's it. And that's it. When r, and this is the leading behavior, when r is large, t is very small, that contributes. This is 1 over square root of t, so this just gives something like square root of r. So this just gives a power of r. So this full integral is convergent and gives just some power of r. If I were to compute it at large radius, dominated by the contribution of small t. Right? So I can just add small t here. I can ignore this. And I get 2m square root exponential that integrates trivially to r to some power. That power is 1/2 in this case, of course, with dimensional analysis. So that's the result that we will get, and the exponential is manifestly outside. Right? So here I could do the trick that Vieira was proposing, which is to rescale t by r. Now I rescale t by r, this becomes e to the minus capital T, this becomes capital T, and I just get the power of r outside. Right? So now if I were to rescale, I could. I rescale t by r, so I get r to the minus 1/2. Do you agree? And then there is no r here. And there is no 2m here. And we just need to do this integral that gives a number. That gives us a number. Now it's just a number. R got out here explicitly. Okay? So that's how we could. And again, it's always the same logic. In Fourier, the basic intuition is, if you are in Fourier, you have an integral in Fourier. You move the contour, and now because you have an imaginary part, the exponential is exponentially decaying. Whatever you are integrating, so whenever you have a function in Fourier, if you are integrating something that is smooth, if I have an integral e to the I kr times some smooth Fourier transform, where this guy is smooth, and by smooth it means, what I mean by this is that I integrate over k, and there are no singularities here, and there is some singularities here. So these are singularities. And this is the real line. The claim is always like this, that, well, let's do just single variable, dk, k, but the generalization is trivial. Okay? So this is what we have. Now I'm telling you some simple mathematics about Fourier. And the claim is, I move the contour, if I want to study at large r, I move the contour here. It's a clever thing, because if I move the contour up, now I get an imaginary part for k, this is exponentially small. So the more I move the contour up, the more exponentially suppressed the integral is. Right? So what matters is the first time I cannot move it up anymore. It's the first singularity in a complex plane. So what dominates is this integral here. And then I have plus this one here. But this one is already higher, so it's much more suppressed than this one. So afterwards I can say that it's this one, and then this. But this is much more suppressed. It comes with a higher imaginary part. So it's always the first singularity that matters. Right? And whatever the position of that first singularity is, this integral behaves as e to the minus a constant times r, where this constant is related to the imaginary part of the first singularity. So singularities in Fourier space govern large distance behavioral correlation functions. That's a very general result of Fourier analysis. Okay? And it's just based on just this. Just you move the contour up, it's exponentially small. So if you can move it arbitrarily, the result is 0. So, but typically you cannot. You have singularities, and you pick the first one, and that gives you the behavior at large distance.
The other way around for small distances is true as well. You go from the farthest singularity to the nearest. Find small r behavior.
At small distance, if this converges, you just put r equals 0, and you need to know the area of this function. So, depends very much on the behavior at large distances, at small distances. Yeah. So no, there is nothing trivial we can say about small distances. It's because large distances, we have these crazy oscillations that become exponential suppressions as we move, that we can say something more. Okay. So we are over time, but I want to mention yet, sorry, but I will I don't want to come back to this because it's just mathematics. I want to ask you what is yet another way that we could estimate a large R behavior. So tell me. So we did it in two ways already. Cartesian coordinates, we see it works. Spherical coordinates, we explained how to do it. And what is the other way that we could do it? To estimate a large radius behavior of this propagator. Guesses, proposals. What else do we know about this propagator? G of I.
Oh, that it's the green function.
Very good. That this is the green function. So we know that this obeys, that this operator is the inverse of that function. So it obeys an equation of the form Laplacian plus m squared g of r. I'm going to write it down and explain, equal delta function of r. I want this equation. So if you don't know what Laplacian is, we can figure it out right now, because what is this delta function of r? Is the integral with this measure without this denominator. Right? So what is this guy doing is removing that denominator. The m squared is there, and this Laplacian is something that gives k squared. So what's this Laplacian? This Laplacian is just minus two derivatives, right? d dx mu, d dx mu. Right? You agree? You take each derivative you take brings down an ik. You take two, you get minus ik. You get ik squared, which is minus k squared. You want plus k squared, you put an extra minus. Right? So how? And now this is the equation that this propagator satisfies. And what's the delta function if r is large? What's the value of the delta function at large radius? It's 0. The delta function is only non-zero if r is 0. So it's 0 at large r. And what's the Laplacian in spherical coordinates? Because this is only a function of spherical coordinates. No, d dimensions.
Oh, the general form of it is 1 over square root of g. So.
But isn't there something like, because of spherical symmetry, the green function will only be a function of the magnitude of r? So
That's right. So this is only function of magnitude of r. So if I write this Laplacian as some radial part plus angular part, I can drop the angular part, right? So and the radial part is what?
dA squared dr squared.
Sorry?
dA squared dr squared.
D squared dr squared, is that? No, that's wrong.
It's 1 over r
This
derivative in r, 1 over r derivative in r.
Right. So that's another thing that you have to clean up. It's r d minus 1 d dr d dr 1 over r to the d minus 1 in the dimensions. Okay. So if you have okay. So that's the Laplacian operator. Okay. Should I explain how we could derive this in a very easy way? Well, let me explain, because okay, it's not 100% derivation, but what is this operator? It has two derivatives in r. The question is these powers of r, right? So in our memory we don't remember. So we are lost in a desert island and we remember it's something like this. There is some power of r that I don't remember, dr, maybe some other power of r, then dr, maybe there is yet another power of r, rc, and that's the operator, right? So it could be something like this, and I don't remember these powers, a, b, c, d, a, b, c, right? So how could we fix this? Well, we know what is delta acting on r squared. Because delta acting on r squared is x squared plus y squared plus z squared plus ta ta ta. And this, right, is just d squared dx1 squared plus d squared dx d squared. So acting on r squared, which is x1 squared plus blah 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 plus xd squared. Each one gives 2, so this should give 2d. Right? So if it should give 2d, what we conclude when we multiply this r squared, this implies, well, one thing which is obvious is that the total power after all these operations should be 0, and that says the trivial thing that a plus b plus c is 0. And that's obvious because you already have two derivatives in r, so the dimensions are already good. Right? But that's so that the total result is a constant. And to get a prefactor of 2d, we conclude that 2d equal, well, what would it be? It would be c plus 2 from the first derivative, and then b plus c plus 1. Right? Yes?
Can you explain it again? Laplacian times.
Tudo bom.
Você vai ficar aqui lascar tudo, daqui a pouco o exame que vai ter aqui.
Deixa quanto tempo?
Chegou 1h15, já estão chegando os alunos.
Tá bom, só mais 15 minutos, pode ser? 10 minutos?
10 minutos tá.
Tá bom, 10 minutos. So, yes? Who was asking a question? Yeah? So, the Laplacian is this in Cartesian coordinates by definition, right? And I want to know how to translate it into radial coordinates. Right? But what is r squared? R squared is just x1 squared plus xd squared. So acting on r squared is trivial, just this acting this, each one gives 2. Right? And that gives these equations. And there is another equation you could get very easily, but since we are being asked to leave, I'll just write the result here. So I act, it would be 4d plus 8 equal c plus 4, b plus c plus 3. And this equation that we would write here would be from the condition that the Laplacian acting on r to the 4 equal to the correct thing, that should be 4d plus 8 times r squared. You can easily also, it's very trivial to just immediately realize. And if you have these three equations, this fixes the Laplacian to be this particular one. Okay? So now, what you can do is, you want to act with the Laplacian, 1 over r to the d minus 1, d dr, r to the d minus 1, d dr minus m squared. Right? And you act on this on an ansatz. You make an ansatz and you say that I act on g, I want to get 0, and you say that my g of r, I could approximate it by, say, some constant alpha r to some power beta e exponential of minus gamma r to some power delta, for example. Okay, the constant you are never going to fix because it's homogeneous, but you would write an ansatz like that, plug it into this differential equation and find out the various constants. Okay? So you plug this here and you would conclude that delta equal to 1, you would find that gamma equal to m, and you would find that beta is something like d minus 1 over 2 or something like this that you would have to work out. And that's yet another way of finding the large distance propagator from the definition as a Green's function. Okay? So, yeah, so for example, here is another thing to clean up, here is another thing to clean up, here is another thing to clean up. So by no means I'm giving you all the details, but I think you can also, you can check why this factor here, you can check this equation more carefully and this, but everything, all the ingredients are in the blackboard. So do make sure that you understand the large distance behavior of this propagator without any difficulties, so that then we conclude with the Gaussian model. We understood the relation to random walk, we understood the propagator, and we saw that it decays exponentially with distance. So that means that as the spins separate a lot, they no longer feel its influence on each other, and their correlation just vanishes and goes to zero. Right? So that's what we expect physically, and it's exponentially fast. And therefore, spins, if they are separated, they really don't feel each other. So how could we imagine getting a behavior that's not exponentially fast, that's not exponentially decaying?
For interactions
Which what?
allowing for longer interactions.
Long range interaction would be an option, but that's too easy. Of course, if I put a long range interaction, of course the spins interact long range, that's okay. But why is it's exponential decaying? With what is controlling this exponential? The mass. So m, this meaning is a mass. So if m is a parameter, because in my lattice m was coming from u and t. If there is a point where m goes to 0, then I lose the exponential decay and I get a power law behavior. That is a phase transition. That's a critical point. It's the point where the correlation length, which is by definition this m, goes to infinity. Correlation length is 1 over m. Or the effective mass goes to 0. Okay? So that would be the meaning of a phase transition. And we'll study that next time. Okay, we can stop recording now.